Hi everyone, let me see, I can see all. I'm Melvin. In this presentation, I'm going to talk about an evolutionary algorithm called Imperialist Competitive Algorithm. Um, this paper is titled Imperialist Competitive Algorithm with an extra term, an algorithm for optimization inspired by imperialistic competition. This is the paper I picked by the following authors. It was presented back in September 2007 in Singapore in an IEEE Congress on Evolutionary Computation. And so far, it has over 3,600 citations, which is pretty good, awesome reason for talking about it today. Before we move on, I have to say that my presentation is not just based on that specific paper. It's more like a lecture based on a couple more papers to cover that specific algorithm. So you might come across some new topics here, but don't be surprised. It's all part of that ICA algorithm, but a little bit hidden on that original paper. I think you can, yeah. As you can tell, every kind of evolutionary algorithm is based on most of them are based on some natural phenomena. This specific algorithm is based on imperialism, on imperialist behavior in history. Let's start by the definition of the imperialism. The word imperialism is basically when a country extends its power beyond its borders. This can happen through direct control or more subtle means like dominating markets for goods or resources. But no matter how, it's basically they try to compete, the imperialists try to compete over their other enemies or lands to make their own nations more powerful and destroy the weaker ones. There's an example here. Let's take the 18th century competition between France and Britain over India. At the end, Britain came out on top and established its control over the country in India. And once they settled in, they tried to reshape the local customs. They tried to set up English-speaking schools, like they built roads, railways, telegraph lines, just to keep India close to their nation or to themselves. So, being that said, let's go over the workflow and a flowchart of how the imperialistic or imperialist competitive algorithm itself works. As depicted in this flowchart, it all starts with an initial population, which we think of it as a country in this specific algorithm, countries of a world. From this group, some of the strongest countries are chosen to be the imperialists, and some other will become their colonies. It depends on their power. There will be some sort of fitness evaluation, like the things we do on genetic algorithm, to evaluate which one has the most power and which one has the least, so that they can get divided into two categories of colonies and imperialists. And then it's time to calculate the total power. As I said, in this specific paper, they decided to calculate this based on the power of the imperialist itself and a fraction and a percentage of the mean power of the other colonies of that imperialist. After that, the competition starts. It's all about the competition in this algorithm. And the process continues. This competition continues and continues until they reach a convergence, which they mean by convergence, they mean that the only one empire is left at the end, and all other countries or colonies will become the colonies of that specific empire. That's an ideal scenario. All the colonies have the same position in that ideal world, and they all have the same power. They're all under one flag, and that's the end of the competition and of the war, actually. So as you can see, the algorithm consists of a lot of different steps, which I will go over each of them in next slides. First step is to generate initial empires. Like the genetic algorithm, we have some sort of arrays here. In genetic algorithm, we call it as chromosomes. Here we call it as countries. We have an array of variables, like this one here in this picture. Each country has some sort of properties like culture, language, economy, and some other things that finally the power of or cost of that country will be determined by the cost function based on those variables. So, for example, if we use the sphere function for evaluation, the power of a country would be the sum of the square of each property. As you can see in this example, it becomes like 90. Yeah. But of course, we can switch these functions and use other kind of functions like Rosenberg, Himmelblau, as we discussed that in the class, rest region. It depends on what we want to analyze. Yeah. Now each country has a power value assigned to it. Depending on the problem, we will pick either the top or the bottom percentile of the sorted list of the countries with their power. The remaining colonies are then randomly assigned to those specific big imperialists, and as you can see in this figure, the bigger ones end up with more colonies, and the weaker ones have fewer ones. The colonies of the same imperialists are being shown with the same color. For example, these colonies belongs to this specific red imperialist. Next step is assimilation. As I mentioned earlier, imperialist countries try to improve their colonies. So in each iteration, the colonies move toward their imperialists by a random amount we call here as X in this representation. However, history always tells us that they cannot observe fully, so they partially observe to the imperialist countries. So there must be some sort of deviation in this assimilation process, which they showed that with theta. Here, I guess, yeah, if you can see it here, yeah. Okay, there are two other symbols here, as you can see, a beta and a gamma. These are arbitrary parameters in algorithm. Beta indicates how exploitative the colonies are in the space behind their imperialists, and the gamma reflects how exploitative the colonies are as they travel toward their imperialists. This is a little bit complicated, but those explanations are a little bit more fluent that we can refer to. The authors claim that setting beta to about 2 and gamma to about pi divided by 4 radians could tend to get a good convergence to the countries, not to get into the global optimum, global minimum. But this is definitely something that we can talk about, predefined numbers. If a country or a colony randomly changes position based on some kind of randomizations instead of being assimilated by an imperialist, that's what we call revolution. Do you have any idea what would be the equivalent of revolution in the genetic algorithm program? Genetic algorithm, do you have any idea? I just try to engage you in the conversation. That's
when it moves to a different, like it moves its sort of home to a colony?
Yeah, just like without, just not following the same path of doing the things, like a mutation. This is the equivalent of a mutation in genetic algorithm. There are a lot different things between revolution and mutation, and both of them helps increase the exploration and prevent the early convergence to local optimum. In this figure specifically, if a colony is at point A here, it might move to a point between A or B through assimilation, but that could trap it into a local optima. So when they perform some sort of revolution in this implementation, the colony can suddenly jump from point A to point C, which allows it to escape from the local optimum. The next step is exchange process. After the assimilation process and the revolution operations, we compare the cost functions of the new positions of the colonies with the cost function of the imperialist. If we find any colony with a lower cost function than the imperialist, we swap the imperialist with the colony, and of course vice versa, just to keep it into a better position. Uniting similar empires. As imperialists and colonies move toward the global minimum, if two imperialists get too close to each other, of course within a certain threshold, they will merge into one new empire, and their colonies will combine under that new imperialist. The power of an empire is calculated based on the power of its imperialists and a fraction of the power of its colonies. Here, in this formula, we will have some sort of alpha, which is a positive number between 0 and 1, that they claim that it's typically better to keep it close to 0, which a smaller alpha means that the imperialist power has a greater impact on the total power of the empire, and a larger alpha means that the power of the nations is much more important in the total power. It's competition time. All empires are now trying to race to take control of the weaker colonies from each other. As the stronger empires gain more power, the weaker ones start to somehow dissolve in the whole process or fade away. In this imperialistic competition, we focus on the weakest colonies from the weakest empires. Then all the other colonies try to just take control of those weak colonies or countries. Each empire has a chance to take and claim that colony, but it's not 100% guaranteed. Let's put it in this way. How does it exactly work? Do you remember the roulette wheel in the genetic algorithm? Yeah, that's pretty slow and computationally heavy equivalent of this for this operation. Instead, they used a probability density function, or PDF, which is much more faster and not that computationally heavy, a little bit efficient. So there are some sort of specific details about how this process is going to happen, but which I'm not going to talk about those technical details. But there are some sort of normalization and probability calculation that resulted in a index score at the end, which is the chance of an empire to get selected to conquer that specific weak colony. Let's think of it like a lottery. For example, the more chances of the more chance cards you buy, the better your odds of winning, right? But it's not 100% guaranteed. So if we have a bigger and most powerful empire here, the chance of getting that weaker colony by that specific empire is higher, but it's not 100% guaranteed. Clear? Do you have any specific question so far? Sounds good. Okay. As expected, weaker empires gradually lose their colonies to stronger ones and make those strong colonies much more powerful, and those weaker ones will collapse at the end, solve this over time. Eventually, and at the end, the strongest empire will take over and all the others will collapse, as I said. And in this ideal world, every colony and imperialist will be treated equally or equal, because they're all under the same flag and the same power. And that's what, when we end the process and end the competition and the algorithm stops. Now it's a good time to take a look at a demo, I guess. Actually, this is a visualization based on a JavaScript code available on GitHub. So in this plot, let me stop it here. In this plot, the bigger dots, like this one, are the imperialists, and like those, the capital of the empire, the one with the highest costs or power. And the smaller ones are their colonies, all in the same color, like this. You'll see that the colonies getting close and close to their imperialists over time. If a colony figures out a better solution along the way, it can eventually change its position. That's the whole idea behind the exchange process that I said. You may already notice some exchange things here. On the other side of the screen, we have some key parameters here. First up, we have alpha, beta, and gamma, which we touched on earlier. There are some other customized fields like number of nations, empires, and iterations, which I will we'll stick with the default settings for this presentation. And then, if I change this, we have some sort of functions here. The evaluation function is also flexible here, so we can choose from rest region, Ackley, sphere, Rosenberg, Himmelblau, and even we can add any other custom formula for the evaluation. Let's speed up the process to see what will happen at the end. Let's stop it here. Do you have any idea who will come at the top between these four empires in this round? Any guesses? It's not 100% guaranteed to. It's just a guess. Let's resume. Sometimes there are some sort of tight competition between these two, the last two empires, and sometimes, because this representation lacks the implementation of revolution, I guess, sometimes it gets stuck into the local optima, and those two last remaining empires just compete and compete and compete, and no one won at the end. So, yeah. But if we implement the revolution, I think it's not going to happen. But a good chance, of course. I'm almost done here. This slide is more for a brainstorming or discussion thing. I'd love to hear your thoughts about any improvement that can happen for this algorithm. I've got a couple in the next slides, but I'd like to know if you have any kind of suggestions or any ideas to share. Do you have any? It's not yet over. Let's continue. Yeah. One thing to consider is the performance of any metaheuristic algorithm like the ICA, which we touched on here. It really depends on how well we tune its parameters. What if we can tune them over time? There are lots of ways to do that. For example, we can use reinforcement learning or probably some other methods so that the parameters can adjust dynamically based on the state of the colonies during the evaluation process. That was the first idea. There is another idea, which is about the initial setups in ICA. Right now, we know that the ICA and the imperialist is the strongest country with the highest or the best fitness function. And all the other countries or colonies need to move toward it, right? So this is like a greedy strategy. So if the imperialists get stuck into a local optimum, the colonies have a hard time to collapse or escape from that specific trap. You can call it trap. It might be better to find a way for the colonies to learn not just from that imperialist, for example, also to learn from other countries on that empire so that to avoid getting them into the trap. This is also achievable by using differential equation and some steps of mutation and crossover steps. Actually, one of those 4 references that I've mentioned in the earlier slides implemented this specific idea, and they achieved a good result in comparison to the basic ICA. All right, hope you picked some good stuff about the computation. If you have any questions to take answer, I'd be happy to do so. Questions? Any questions? I think that was much. Yeah. You can go.
Is this good for like problems other than, I guess those like 2-dimensional optimization problems, or three-dimensional?
This is a specific algorithm. You mean in comparison to the other ones?
Just like, or I guess can be applied to other kinds of algorithms.
Honestly,
Or other kinds of problems.
yeah, I think that there should be some capabilities to do so, but I'm not sure. Actually, they evaluate one of the other papers compared this specific algorithm with some other state-of-the-art methods of that time, and not right now. And if it's possible, I can show it even to you. This is not. Yeah. I think this is. Yeah, I think it's the one. It compares the properties of the ICA in terms of search space, local searches, and other even computational costs to the genetic algorithm, simulated annealing, taboo search, and colony optimization, particle storm optimization, and the specific ICA. And they found that this algorithm can achieve a good amount. I mean, it achieves much better results in comparison to other ones, and it's applicable on several kind of problems, I guess, according to my understandings. Yeah, I think it's possible.
This kind of answers my question, which was, can you apply this algorithm to different representations?
Yeah.
Like your example was continuous optimization, but could you evolve computer programs with this?
On that algorithm.
Yeah. Like this slide seems to suggest you can, because it's listing different problem representations.
Yeah, I think it's possible. But if you ask me how, I have no idea how to just adjust it. But it seems to be possible. Yeah. At least it's supposed to be possible, according to these papers. Yeah. Do you know it yourself?
No, I'm not familiar with ICA. But I'm just wondering how you can encode countries. I don't know how the search operators would work.
There's not much info about this, the specific detail of the code implementation, at least on the specific paper. But there are several GitHub implementations, like the one that I've used here, which have some good hints on how to do so. Let me just bring it up here. Yeah, this was the one. I think there must be some sort of WikiHow or docs here to understand how to change the parameters and adjust it for the customized for a desired sort of problems. Yeah.
Cool.
If you have any other questions, I'm here to answer. Otherwise, I'm done. Thank you so much for your attention.